In the glow of 1,000 computer screens, across boardrooms in California and government halls in Washington, a single image repeats itself like a prayer. Gleaming domes rise from rust-colored dust. Solar panels stretch toward a pale sky. Human figures in sleek suits walk confidently across a transformed world. Mars, they call it. Not as it is, but as we dream it might become. A second Earth, a backup plan, a destiny written in the stars themselves. Yet behind these renderings, behind the billion-dollar budgets and the carefully orchestrated press conferences, there exists another Mars. Not the Mars of artists and visionaries, but the Mars of physics, chemistry, and biological reality. A Mars that scientists discuss in hushed tones during conference coffee breaks. A Mars that appears in classified reports marked with careful qualifications and concerning footnotes. A Mars that, when examined without the lens of hope and human ambition, reveals a truth far more challenging than most are willing to acknowledge. Tonight, we will cross that threshold between dream and data. We will trace the invisible lines that separate what we wish Mars could be from what it actually is. Not to crush wonder, but to honor it with honesty. Not to end exploration, but to understand what we are truly exploring. Because the question is not whether we want to live on Mars. The question is whether Mars will ever allow us to. The investment is staggering. Government space agencies allocate billions. Private corporations pledge fortunes. Timelines are announced with confidence. Decades collapsed into years through sheer force of optimism. We are told that children alive today will walk on Martian soil. That permanent settlements are not a question of if, but when. That humanity's future as a multiplanetary species begins on that distant red world, forth from the sun, glowing like an ember in our night sky. But what if the obstacles are not engineering problems waiting to be solved? What if they are fundamental barriers written into the nature of Mars itself? What if the gap between our Mars colonies in fiction and Mars colonies in reality is not a matter of technology or funding, but of biology, physics, and timescales that dwarf human civilization? This is not a story of failure, it is a story of honesty, a careful examination of what separates aspiration from possibility, from the radiation that sleets invisibly through Martian skies to the atmospheric pressure that makes every breath a technical challenge. From the water locked in toxic soil to the gravity too weak to sustain human bones. From the mental isolation of a world with no rescue to the economic equations that refuse to balance no matter how the numbers are arranged. We will walk through these realities not as skeptics, but as seekers of truth. We will examine the science that exists beyond the headlines, spoken by researchers who have spent careers studying planetary habitability, human physiology in space, and the brutal mathematics of interplanetary survival. And in doing so, we may discover something unexpected. Not that humanity has no future among the stars, but that our future might lie in directions we have not yet had the courage to imagine. If you are listening to this in the quiet hours, when the world around you sleeps and your mind drifts toward larger questions, leave a comment below. Tell us where you are watching from and what time it is in your corner of our shared world. There is something profound about knowing we are all gazing upward together from different longitudes and latitudes, united by curiosity and the ancient human need to understand our place in the cosmos. Now, let us begin. Let us travel not to the Mars of imagination, but to the Mars that waits in reality, patient, ancient, and utterly indifferent to our dreams. The journey starts not with rockets and spacecraft, but with something far more fundamental, with invisible particles streaming through space at nearly the speed of light, carrying a danger that no amount of engineering has yet learned to stop. We arrive at Mars with dreams of red deserts and new frontiers, but before we even step onto its surface, we encounter an enemy that cannot be seen, cannot be touched, and cannot be escaped. Radiation, not the kind that comes from microwave ovens or cell phones, but the deep, penetrating cosmic radiation that has bathed Mars in an invisible storm for billions of years. This is not simply a hazard to be managed. It is a fundamental reshaping of what human life would mean on another world. Earth is protected by an invisible shield, one we rarely think about but depend upon every moment of our lives. Our planet's magnetic field, generated deep within its molten iron core, extends thousands of miles into space, deflecting charged particles from the sun and cosmic rays from distant supernova. This magnetosphere is why life flourished here. Why complex organisms could evolve without their DNA being shredded by radiation from space. Mars once had such a field. Ancient rocks preserve the memory of it, magnetic minerals frozen in time, pointing in directions that no longer exist. But roughly 4 billion years ago, Mars's core cooled. The dynamos stopped, the magnetic field collapsed, and ever since, Mars has stood naked before the cosmos. The numbers are not abstract, they are visceral. On Earth's surface, we receive an average radiation dose of about 0.3 millisieverts per year from cosmic sources. On Mars, that number climbs to approximately 60 millisieverts per year, more than 200 times higher. A single year on Mars delivers the radiation exposure equivalent to roughly 30 chest X-rays every week, continuously, without pause. This is not a spike or an event. This is the baseline, the normal background hum of existence on a planet without protection. But radiation exposure is not like other dangers. It does not announce itself with pain or immediate symptoms. Instead, it works silently at the molecular level, slicing through DNA strands, disrupting cellular machinery, triggering mutations that accumulate over time. Some of these mutations are repaired by the body's remarkable healing systems. Others are not. The damaged cells may die, or they may survive, replicating their errors, passing them forward. Over months and years, the probability mathematics become unavoidable. Cancer risk increases. Cardiovascular damage accelerates. Cataracts form. Cognitive function may decline. The human body, evolved over millions of years beneath Earth's protective cocoon, is simply not designed for this environment. The brutal math of radiation exposure tells a story that is difficult to ignore. Studies estimate that during a round-trip mission to Mars, including time spent on the surface, astronauts could receive doses approaching 1,000 millisieverts or more. At these levels, the lifetime risk of fatal cancer increases by approximately 5% or higher. For a crew of 6, statistically, that could mean losing someone not to an accident or equipment failure, but simply to the accumulated cost of being there. And these calculations assume relatively short missions. For permanent settlement, the numbers compound year after year. A child born on Mars would begin accumulating radiation damage from birth, their cells dividing and growing under constant bombardment, their future health outcomes unknown, untested, unprecedented. The immediate solution seems obvious. Go underground. If the surface is hostile, live beneath it. Mars has lava tubes, ancient channels carved by flowing magma, potentially large enough to house entire settlements. Underground habitats would provide meters of rock overhead, shielding inhabitants from the worst of the cosmic radiation. In theory, this is elegant. In practice, It presents challenges that stretch the limits of engineering and human psychology. Building underground on Mars is not like building a basement on Earth. Every cubic meter of excavation requires energy, machinery, and time. Equipment must be transported from Earth or manufactured in situ from Martian materials, a process that itself requires massive infrastructure. Support structures must prevent collapse in a world where seismic activity is unknown and long-term geological stability is uncertain. Life support systems must function in enclosed spaces with no natural ventilation, no sunlight, and limited options for expansion or escape. Even if we overcome these engineering obstacles, we face a more insidious problem. The sheer mass required for effective radiation shielding is staggering. A habitat designed to reduce radiation exposure to Earth normal levels would need walls several meters thick, constructed from materials that are either imported at immense cost or manufactured on Mars using processes we have not yet perfected. Water, with its hydrogen-rich composition, is an excellent radiation shield, but Mars's water is locked in ice and scattered across the planet. Regolith, the loose Martian soil, can provide some protection, but moving and compacting thousands of tons of it requires resources, machinery, and time measured not in weeks, but in years or decades. Current shielding technology, developed for spacecraft and the International Space Station, relies on materials like polyethylene, aluminum, and composite structures. These reduce radiation exposure, but do not eliminate it. More advanced concepts, such as electromagnetic shielding that would mimic Earth's magnetic field on a local scale, remain theoretical, energy-intensive, and far beyond our present capabilities. The gap between what we need and what we can build is not small. It is vast. And then there is the psychological dimension, a cost that cannot be measured in millisieverts or structural integrity. Imagine living your entire life underground. No sunlight filtering through windows, no sky overhead, no horizon to gaze upon. Days measured not by the movement of the sun, but by artificial lights on timers. The surface of Mars, with its sweeping dunes and towering volcanoes, would be visible only through cameras or brief, heavily shielded excursions. The very thing that draws us to Mars, its alien landscapes, and the promise of walking on another world, would become something forbidden, glimpsed only in passing, never truly experienced. Humans did not evolve for such confinement. Studies of long-term isolation in submarine crews, Antarctic research stations, and simulated Mars habitats reveal patterns of stress, depression, interpersonal conflict, and cognitive decline. These are environments with the promise of eventual return, the knowledge that isolation is temporary. On Mars, there is no temporary. The radiation is always there, waiting on the surface. To live on Mars is to live in permanent shelter, not from storms or cold, but from the universe itself. Some researchers propose rotating crews, limiting surface time, and designing habitats with maximum psychological support. Virtual reality windows that simulate Earth's skies. Rotational assignments that allow periodic returns home. But each of these solutions adds complexity, cost, and dependency on Earth. They also acknowledge an uncomfortable truth. Mars is not a place where humans can thrive freely. It is a place where survival demands constant vigilance, constant trade-offs, constant awareness that the environment is fundamentally hostile. The radiation problem is not unsolvable in a strict engineering sense. With enough resources, enough infrastructure, and enough time, we could theoretically build habitats that reduce exposure to manageable levels. But manageable is not the same as safe. It is not the same as thriving. And it raises a question that echoes through every proposed solution. If we must retreat underground, live in artificial environments, and spend our lives shielded from the world around us, what exactly are we gaining by going to Mars? What does it mean to call a planet home if we can never truly inhabit its surface? Radiation on Mars is not just a technical challenge. It is a reminder that some environments, no matter how alluring from a distance, are not meant for human life. The universe does not bend to our ambitions. It operates by laws indifferent to our dreams. And Mars, beautiful and ancient as it is, remains a world where the very air, or lack of it, is only the beginning of the dangers we would face. As we imagine ourselves standing on the Martian surface, boots pressed against rust-coloured soil, we confront a reality that no photograph from orbit can convey. The atmosphere itself is hostile, not in the dramatic way of Jupiter's storms or Saturn's winds, but in a quiet, relentless manner that makes every breath impossible and every moment outside shelter a calculated risk against invisible forces. Mars possesses an atmosphere, but to call it such feels almost generous. What envelops this planet is more accurately described as a whisper of gas, a memory of what an atmosphere might be, composed of 95% carbon dioxide, with traces of nitrogen and argon. It creates a blanket so thin that standing on Mars would feel less like standing on a planet and more like floating at the edge of space itself. The atmospheric pressure on Mars averages just 0.6% of Earth's. To understand this, imagine ascending to nearly 100,000 feet above Earth's surface, higher than any aircraft flies, to altitudes where the sky turns black and the curvature of the planet becomes visible. That is the pressure you would experience at sea level on Mars. The human body was not designed for near vacuum conditions. At such low pressures, the physics of liquids changes in ways that are profoundly dangerous. Water boils at approximately 50 degrees Fahrenheit on Mars. This means that any moisture exposed to the Martian atmosphere, saliva, the fluid on your eyes, moisture in your lungs, would begin to boil and evaporate almost immediately. This phenomenon, known as ebulism, causes tissues to swell as dissolved gases come out of solution. Blood does not boil in the dramatic sense often depicted, protected as it is within the circulatory system, but the effects are catastrophic nonetheless. Within 15 seconds, unconsciousness would follow as oxygen depletes from the brain. Within 2 minutes, death would be nearly certain. This reality transforms every moment on Mars into a fragile dependence on technology. A pressure suit becomes not just equipment, but a personal atmosphere, a miniature Earth wrapped around your body. The suit must maintain constant pressure, regulate temperature, provide oxygen, and remove carbon dioxide, all while allowing enough mobility to perform tasks. And here lies one of Mars' most psychologically taxing truths. A single tear, a failed seal, a puncture from a sharp rock represents not just equipment failure, but immediate mortal danger. On Earth, we live with the luxury of assuming our next breath. On Mars, every breath is a technological achievement, and the atmosphere is constantly waiting for that technology to fail. Then there is the dust. Mars is not just a world with dust, it is a world defined by dust. Martian soil, called regolith, blankets the entire surface in a fine powder that clings to everything it touches. Under microscopes, this dust reveals sharp, jagged edges. Unlike Earth's dust, which has been worn smooth by wind and water over eons. But the physical characteristics are merely the beginning of the problem. Martian soil contains perchlorates, chlorine compounds that are highly toxic to humans. Perchlorate concentrations in Martian soil measure up to 0.5% by weight, levels that would be considered hazardous waste on Earth. Perchlorates interfere with the human thyroid gland, disrupting hormone production, essential for metabolism, growth, and neurological development. They are easily absorbed through skin, through ingestion, or through inhalation. And here is the insidious nature of Martian dust. It gets everywhere. Astronauts who walked on the Moon, which has similar fine dust properties, reported that lunar dust infiltrated sealed containers, scratched visors, and clung to suits despite vigorous brushing. On Mars, this toxic dust would coat solar panels, work its way into habitats through airlocks, contaminate food and water supplies, and require constant, exhausting vigilance to manage. The dust does not remain politely settled on the ground. Mars experiences dust storms that dwarf anything Earth can produce. Local dust storms can grow into regional events, and occasionally, every few Martian years, the entire planet becomes shrouded in a global dust storm. These planetary-scale tempests can last for months, blocking up to 99% of available sunlight. The storm that effectively ended NASA's Opportunity rover mission in 2018 persisted for months, denying the solar-powered rover the energy it needed to survive. For human settlements dependent on solar power, these storms represent not dramatic danger, but slow suffocation. Imagine living in a habitat where for 3 or 4 months you receive almost no solar energy. Battery reserves deplete. Systems must be powered down. Life support operates on minimum settings. Temperature drops as heating systems conserve power. The psychological weight of living in darkness, knowing that your life depends on stored energy slowly draining away, transforms every day into a countdown. Some propose that nuclear power would solve this challenge, and indeed, nuclear reactors or radioisotope thermoelectric generators could provide consistent energy. But these systems add complexity, mass, and cost to missions already stretched to the limits of feasibility. They represent not simple solutions, but trade-offs, exchanging one set of vulnerabilities for another. As we contemplate these challenges, perhaps the most disheartening realization emerges when we consider terraforming, the theoretical process of transforming Mars into an Earth-like world with a breathable atmosphere. Popular imagination often treats terraforming as an engineering challenge, difficult but achievable within a few generations. The reality is far more humbling. To terraform Mars would require dramatically increasing its atmospheric pressure and fundamentally altering its composition. This would mean releasing vast quantities of gas, nitrogen, oxygen, and greenhouse gases to thicken the atmosphere and warm the planet. Some proposals suggest melting the polar ice caps, which contain frozen carbon dioxide, to release CO2 and trigger a warming feedback loop. Others imagine importing volatile compounds from asteroids or constructing enormous orbital mirrors to concentrate sunlight. Even under wildly optimistic scenarios, with technologies we do not currently possess deployed at scales we have never attempted, terraforming Mars would require not decades or centuries, but tens of thousands of years. Conservative scientific estimates place the timeline at 100,000 years or longer. This is not engineering. This is geological time compressed into a theoretical possibility. It means that any human who steps foot on Mars, and indeed any human born there for thousands of generations, would live and die in a hostile environment, entirely dependent on technology for every breath, with no hope that their children's children's children for hundreds of generations would experience anything different. Mars's thin atmosphere is not a problem to be solved. It is a fundamental characteristic of a planet that lacks the mass to hold a thick atmosphere and the magnetic field to protect it from solar wind. Mars once possessed a thicker atmosphere, perhaps even oceans, but over millions of years the solar wind stripped it away. This same process would continue working against any terraforming efforts, requiring not just the initial transformation, but eternal maintenance, perpetual rebuilding of an atmosphere that the universe itself is actively removing. We must sit with this reality, not as a reason for despair, but as a call for clear-eyed understanding. The atmosphere of Mars is not merely thin or different. It is fundamentally incompatible with human life in ways that technology can temporarily shield us from but never truly overcome. Every proposal for Mars colonization must begin by acknowledging this truth. We would not be settling a new land, but rather attempting to survive permanently in an environment actively hostile to our existence, wearing artificial atmospheres like eternal armor, forever one equipment failure away from the void. The question then becomes not whether we can survive on Mars. Clearly, with enough resources and determination, we could manage temporary outposts, but whether we should pour our civilization's resources into making a dead world temporarily habitable when other possibilities await among the cosmos. Water is life. On Earth, this truth is so fundamental that we rarely question it. Rivers flow freely, rain falls from the sky. Turn a tap and water appears, endless and pure. But on Mars, water is not a gift. It is a puzzle wrapped in ice, buried beneath dust, and laced with poison. The promise of water on Mars has fueled dreams of colonization for decades. Yet the reality of extracting, purifying, and sustaining a water supply on the red planet reveals challenges so profound they border on insurmountable. Water exists on Mars, but accessing it is not as simple as melting ice. The discovery of water ice on Mars was celebrated as a breakthrough, confirmation that the raw ingredients for life exist beyond Earth. Orbital surveys and rover missions have revealed vast ice deposits scattered across the Martian surface. Some lie within the polar ice caps, massive frozen reservoirs locked at the planet's extremes. Others are buried beneath layers of regolith, hidden just below the surface in mid-latitude regions. From orbit, instruments detect the telltale signatures of hydrogen, mapping ice deposits that stretch for miles beneath the rusty soil. The water is there. The question is not whether Mars has water, but whether humans can reach it, extract it, and survive long enough to use it. The polar ice caps are the most obvious reservoirs. They gleam white against the red terrain, visible from orbit like beacons of hope. But these caps are located at the most inhospitable regions of Mars, where temperatures plunge to -200 degrees Fahrenheit during winter. Establishing a base near the poles would subject colonists to months of near-total darkness, extreme cold beyond anything experienced on Earth, and isolation from potential equatorial landing sites where solar energy is more abundant. Transporting water from the poles to more habitable regions would require infrastructure that does not yet exist. Pipelines across thousands of miles, energy systems capable of powering them, and maintenance crews to repair equipment in lethal conditions. The poles hold water, but reaching it demands a level of technological sophistication and energy investment that remains, for now, theoretical. The more accessible ice lies buried beneath the surface in mid-latitude regions, sometimes just inches below the dusty crust. Rovers have detected these subsurface deposits, and scientists believe that excavating them could be feasible with robotic mining equipment. But even here, the challenges multiply. The ice is not pure. It is mixed with Martian soil, compacted by eons of freezing and thawing cycles. Extracting it requires digging through regolith, heating the mixture to release water vapor, and then capturing and condensing that vapor into liquid form. Every step demands energy, enormous amounts of energy. On a planet where sunlight is weaker than Earth and dust storms can block the sun for weeks, energy is the most precious resource. Water extraction becomes not just a technical challenge, but an energy crisis waiting to unfold. The process of turning Martian ice into drinkable water is deceptively complex. Heating ice requires power. Separating water from soil requires machinery. Purifying that water requires filtration systems, chemical treatments, and constant monitoring. Even if colonists succeed in extracting water, they must then store it, transport it, and protect it from freezing in the thin Martian atmosphere, where temperatures swing wildly between day and night. A single leak, a single malfunction, could mean the loss of weeks or months of labor. Water on Mars is not renewable in the way it is on Earth. There are no rain clouds to replenish supplies. Every drop must be earned, extracted, and jealously guarded. And then there is the poison. Martian ice is contaminated with perchlorates, toxic chemicals found throughout the planet's soil and ice deposits. Perchlorates are salts containing chlorine and oxygen, and they are lethal to human health, even in small concentrations. They disrupt thyroid function, interfere with metabolism, and can cause severe neurological damage over time. On Earth, perchlorates are considered hazardous waste. On Mars, they are everywhere. Studies of Martian soil samples brought back by rovers have revealed perchlorate concentrations far exceeding safe levels for human consumption. The water ice buried beneath the surface is not pristine. It is laced with these compounds, mixed into the frozen matrix like invisible needles waiting to poison anyone who drinks from it. Removing perchlorates from water is possible, but it requires advanced filtration and chemical treatment systems. Reverse osmosis, ion exchange resins, biological degradation. Each method demands equipment, energy, and expertise. A Mars colony would need industrial-scale water purification facilities capable of processing every litre of extracted water before it could be used for drinking, cooking, or agriculture. The systems would need to operate flawlessly, day after day, with no room for error. A failure in purification could mean contaminated water supplies, poison crops, and colonists slowly succumbing to toxic exposure without realizing it until symptoms appear. The dream of simply melting Martian ice and drinking it dissolves when faced with the reality of perchlorates. Even if water extraction and purification are solved, the challenge of conservation looms. On the International Space Station, water recycling systems operate at roughly 93% efficiency. Astronauts drink water reclaimed from their own sweat, breath, and urine, filtered and purified through complex mechanical systems. This 93% efficiency is considered a triumph of engineering, but it is not enough for Mars. A Mars colony would need to achieve recycling rates of 99% or higher to sustain itself over years or decades. Every shower, every meal, every agricultural process would need to recapture and reuse water with near-perfect efficiency. The margin for loss is razor-thin. Lose even 1% per cycle, and over time, the colony's water supply evaporates into the void. Water is not just for drinking. It is the foundation of agriculture, industry, and life support. Growing food on Mars would require vast quantities of water for irrigation. Hydroponic and aeroponic systems are more efficient than traditional farming, but even these methods demand constant water circulation. A single harvest of crops could consume hundreds of litres. Industry, whether manufacturing, mining, or chemical processing, requires water as a coolant, a solvent, and a medium for reactions. Life support systems need water to generate oxygen through electrolysis, splitting H2O into hydrogen and breathable air. Every function of a Mars colony would draw from the same finite, difficult to replenish resource. Water would not be abundant. It would be the bottleneck that determines how many people can survive, and for how long. The scale of water consumption is staggering. A single human on Earth uses an average of 80 to 100 gallons of water per day when accounting for drinking, sanitation, and food production. On Mars, colonists would need to survive on a fraction of that, perhaps 10 to 20 gallons per day, through aggressive recycling and strict rationing. Showers would be rare luxuries. Washing clothes would become a calculated decision. Every action would be measured against its water cost. The abundance we take for granted on Earth would be replaced by a culture of scarcity, where water is more valuable than gold, and wasting a single drop is unthinkable. Some propose importing water to Mars, launching ice-laden payloads from Earth, or harvesting comets to supplement Martian supplies. But the energy and cost of such missions are astronomical. Water is heavy. Transporting it across interplanetary distances would require fuel, time, and resources that dwarf even the most ambitious space programs. The economics do not favor importation. If Mars cannot sustain itself with local water, it cannot sustain itself at all. The water crisis on Mars is not a technical problem waiting for a clever solution. It is a fundamental barrier woven into the fabric of the planet itself. Ice exists, but it is buried, contaminated, and difficult to reach. Extraction demands energy that may not be available. Purification requires technology that must never fail. Recycling must achieve perfection that has never been demonstrated. And through it all, the relentless Martian environment conspires to freeze, evaporate, and reclaim every molecule of water that humans attempt to hold. Water on Mars is not a resource. It is a test, one that asks whether humanity can truly thrive in a place where even the simplest needs become monumental struggles. The answer, written in the frozen silence of the red planet, remains uncertain. We imagine greenhouses on Mars, rows of vibrant green, stretching beneath glass domes, astronauts harvesting fresh vegetables under artificial light. But beneath this hopeful vision lies a question that refuses to answer itself simply. What does it truly mean to grow food in soil that has never known life? The Martian surface is not merely barren. It is hostile to the very concept of agriculture. The rust-colored dust that blankets the planet, so evocative in photographs, is laced with perchlorates, toxic compounds that would poison earth plants and animals alike. These chemicals, useful perhaps for rocket fuel or oxygen extraction, exist in concentrations that make the soil not just infertile, but actively harmful. A seed planted directly into Martian regolith would not simply fail to grow. It would be chemically sterilized, attacked at the molecular level by a world that has no memory of chlorophyll or roots reaching through darkness toward moisture. Some propose treating the soil, washing away the perchlorates, adding nutrients, transforming dead dust into something resembling Earth's living dirt. But the scale of this endeavor reveals itself slowly, like Mars emerging from the morning haze. To support a single human being requires not just a small garden, but approximately 1 acre of productive agricultural land, perhaps more in the absence of Earth's complex ecosystem. For a colony of 100 people, we would need 100 acres of soil, each particle cleansed, enriched, and maintained within an environment that Mars itself fights to destroy. The energy requirements become staggering when examined closely. On Earth, the sun provides free heat, free light, and free energy for photosynthesis. On Mars, where sunlight arrives at less than half the intensity it does on Earth, every calorie of warmth, every photon of grow-light illumination must be generated, distributed, and sustained through systems that demand constant power. These are not small greenhouses warmed by solar panels. These are vast pressurized structures, heated against temperatures that plunge to minus 100 degrees Fahrenheit, their atmospheres maintained at pressures high enough to prevent water from immediately sublimating into the thin Martian air. Consider the architecture of survival. Domed structures or underground caverns filled with artificial air, their transparent surfaces thick enough to provide radiation shielding, yet clear enough to transmit precious light. The structural engineering alone represents challenges that have no precedent. A greenhouse on Earth can afford a crack, a broken pane, a door left slightly ajar. On Mars, a single failure in containment means explosive decompression. The instantaneous loss of atmosphere, crops freeze-dried in seconds as moisture boils away into near vacuum. And within these pressurized chambers, we encounter a silence that earthbound farmers never experience. There are no bees on Mars, no butterflies, no wind carrying pollen from flower to flower. Pollination, that ancient dance between plant and insect, refined over hundreds of millions of years, must now be performed by hand or by machine. Each tomato flower, each cucumber blossom must be individually attended to, touched by human hands or mechanical pollinators, in a process so labor-intensive it transforms agriculture from seasonal work into a continuous, meticulous task that consumes hours of every day. The absence of wind creates another challenge, one less obvious, but equally profound. On Earth, gentle breezes strengthen plant stems, encouraging them to grow sturdy and robust. In still air, plants grow weak and spindly, unable to support their own weight once they bear fruit. Fans must blow continuously, simulating wind that never naturally exists, adding yet another demand to the energy budget that grows larger with each practical consideration. Many point to hydroponics as the solution, a farming method that eliminates soil entirely, growing plants in nutrient-rich water under controlled conditions. Indeed, hydroponic systems can be efficient, productive, and space-saving. They represent some of humanity's most sophisticated agricultural technology. Yet hydroponics does not eliminate the fundamental problem. It transforms it. Instead of requiring soil, we now require vast quantities of liquid water and precisely formulated nutrients, minerals that must be mined, processed, and dissolved in exact proportions. Nitrogen, phosphorus, potassium, calcium, magnesium, iron, and a dozen trace elements in ratios that vary by crop type and growth stage. Where does this water come from? Mars has water, yes, locked in ice at the poles and buried in permafrost beneath the surface. But extracting it requires energy. Melting it requires energy. Purifying it requires energy. Maintaining it in liquid form requires energy. The water budget for a functioning hydroponic farm, capable of feeding even a small colony, demands millions of gallons processed and cycled through systems that must never fail, for crops die quickly without their carefully balanced nutrients. And the nutrients themselves? On Earth, these minerals can be derived from natural sources, mined or extracted from biological waste through composting and decomposition. Mars offers rock and dust, yes, but extracting usable minerals from Martian geology requires industrial-scale mining and chemical processing operations. Every tomato grown on Mars carries within it atoms that were wrested from stone through processes that demand machinery, power, and human labor, measured not in hours, but in continuous operation. The more we examine the practicalities, the more we discover cascading dependencies. Growing food requires power. Generating power requires equipment. Maintaining equipment requires spare parts. Manufacturing spare parts requires raw materials and fabrication facilities. Each solution opens into new requirements, branching like roots in soil. Except these roots reach not toward water, but toward an ever-expanding infrastructure that must be shipped from Earth or manufactured from Martian resources through industrial processes that themselves demand food for their workers, power for their operations, and time measured in decades of development. Yet even if we solve these engineering challenges, even if we construct the greenhouses, establish the hydroponic systems, and maintain them flawlessly, we face a subtler problem: nutrition. The human body requires not just calories and basic nutrients, but a complex array of vitamins, minerals, amino acids, and compounds that are obtained on Earth through dietary diversity. A diet of potatoes, lettuce, and tomatoes, those crops most commonly proposed for Mars colonies, provides survival but not thriving. Vitamin B12, found primarily in animal products. Omega-3 fatty acids, concentrated in fish and certain seeds. Complete proteins containing all essential amino acids in proper ratios. We could supplement with pills, certainly, vitamin tablets and mineral supplements shipped from Earth. But now our food independence dissolves. We are not feeding ourselves from Martian agriculture. We're extending Earth's supply chain across 40 million miles, dependent on regular shipments to prevent scurvy, rickets, anemia, and deficiencies that accumulate silently until they manifest as illness, weakened bones, compromised immune systems. Some envision bringing animals, establishing protein sources through chickens, fish, or even larger livestock. But animals require food themselves, and in ratios that multiply the agricultural burden. A chicken must consume approximately 2 pounds of feed to produce 1 pound of meat. Fish are more efficient, but require carefully controlled aquatic systems. The energy and space requirements scale geometrically, not linearly. To feed animals that feed humans requires not 1 acre per person, but several, all maintained within pressurized, heated, artificially lit environments on a world that offers none of these conditions naturally. The dream of Martian greenhouses, of colonists harvesting fresh vegetables while red dust swirls beyond transparent domes, is not impossible. But it is not simple. It is not a matter of bringing seeds and planting them in Martian soil. It is the construction of an entirely artificial ecosystem, a manufactured biosphere sustained through constant human effort and industrial-scale energy expenditure. Every meal on Mars represents a victory over a world that offers only stone and cold and silence. Perhaps this is why the images of Martian agriculture feel more like science fiction than practical planning. Not because the technology doesn't exist, but because the scale of effort required transforms farming from something natural into something heroic. On Mars, growing food is not agriculture. It is a form of continuous engineering, a battle against entropy fought with every harvest, every pollinated flower, every gallon of water wrested from ice, and cycled through systems that cannot afford to fail. In the stillness of these imagined greenhouses, surrounded by technology humming with necessary life support, we might pause to consider: on Earth, food grows. On Mars, food must be made to grow, sustained against the planet itself, maintained through effort that never ceases. The difference between these two realities is not merely technical. It is the difference between living on a world and living against one. We arrive on Mars carrying with us the full weight of Earth's gravity. a force so constant we forget it is even there. It shapes every movement, every breath, every heartbeat. Gravity is not merely a phenomenon we experience. It is woven into the architecture of our bodies, into the density of our bones, the strength of our muscles, the rhythm of our cardiovascular systems. On Mars, that architecture begins to collapse. Mars pulls at us with only 38% of Earth's gravitational force. At first, this seems liberating. Objects feel lighter. Movement requires less effort. You could jump 3 times higher than on Earth, leap across vast distances with ease. In those early days, low gravity might feel like freedom. But freedom from gravity is not liberation. It is erosion. The human body, shaped by millions of years of evolution under Earth's pull, interprets low gravity as a crisis. Without the constant stress of supporting our own weight against Earth's 1G environment, our bodies begin an involuntary process of optimization. They shed what appears unnecessary. Bone density starts to decline almost immediately. Astronauts on the International Space Station lose approximately 1 to 2% of their bone mass every month in microgravity. On Mars, with its 0.38 g, the loss would be slower but relentless. Month after month, year after year, calcium leaches from the skeleton, expelled through urine, leaving bones porous and fragile. This is not a temporary condition that reverses with exercise. This is permanent physiological restructuring. The bones of Mars colonists would become lighter, more brittle, adapted to a world with less gravity but catastrophically unsuited for any return to Earth. A fall that would bruise on Mars could shatter a femur. A stumble could fracture a spine. The skeleton itself becomes a prison, trapping its occupant on the world that weakened it. Muscle atrophy follows the same inexorable path. On Earth, simply standing upright requires constant muscular engagement. Our calves, our core, our back muscles all work continuously against gravity's pull. On Mars, that work diminishes. The body, efficient by nature, begins to dismantle what it perceives as excess tissue. Muscles shrink. Strength fades. Astronauts aboard the ISS exercise for 2 hours daily just to slow this deterioration. On Mars, settlers would need similar regimens indefinitely, fighting their own biology every single day simply to maintain a fraction of their Earth strength. But perhaps the most insidious changes occur within the cardiovascular system. On Earth, your heart pumps against gravity, pushing blood upward from your legs to your brain with every beat. This constant work keeps the heart strong and the vascular system calibrated. In low gravity, blood distribution shifts. Fluids migrate toward the head, creating the puffy-faced appearance seen in astronauts. The heart, no longer required to pump as vigorously, begins to atrophy like any underused muscle. Blood vessels lose their tone. The autonomic systems that regulate blood pressure recalibrate to Mars normal. What happens if someone adapted to Mars gravity attempts to return to Earth? Their weakened heart would struggle to pump blood against 3 times the gravitational force they've grown accustomed to. Standing upright could cause blood to pool in the legs, starving the brain of oxygen. Fainting, dizziness. In severe cases, cardiac failure. The journey home becomes physiologically impossible, not because of the distance, but because the human body has fundamentally transformed into something that can only survive on Mars. The inner ear presents another profound challenge. This small labyrinth of fluid-filled canals governs our sense of balance, our spatial orientation, our ability to navigate the world without thinking. It evolved under Earth's gravity. calibrated to detect acceleration and orientation in a 1G environment. On Mars, these systems would be receiving signals they were never designed to interpret. The initial adjustment period might last weeks or months, during which colonists would experience constant vertigo, nausea, spatial disorientation. Even after adaptation, the vestibular system would be permanently recalibrated to Martian gravity, making any return to Earth not just difficult, but potentially incapacitating. Then we arrive at perhaps the most troubling question of all. What happens to children born on Mars? A fetus developing in low gravity faces an environment unprecedented in human evolutionary history. Every stage of development, from the formation of bones, to the growth of muscles, to the wiring of the vestibular system, occurs under conditions no human has ever experienced. Will their skeletons develop properly? Will their hearts grow strong enough? Will their bodies know how to interpret gravity at all? Some scientists theorize that children gestated and born on Mars would be Martians in the truest sense. Their bodies would be adapted from conception to low gravity, their bones lighter, their muscles configured differently, their cardiovascular systems calibrated to 0.38 G. They might be taller, their frames stretched by reduced gravitational compression. They might move with a fluid grace impossible on Earth. But they would also be exiles, unable ever to visit the ancestral home of humanity. Earth's gravity would be crushing to them, literally unbearable. A Martian child brought to Earth might not survive the journey, their heart unable to sustain the increased workload, their skeleton unable to support their own weight. We do not know if human pregnancy is even viable in low gravity. No mammal has ever been conceived, gestated, and born in anything less than Earth's gravitational field. Early studies with animal embryos in microgravity have shown concerning results. Developmental abnormalities, changes in cellular division, alterations in gene expression. These are preliminary findings, hints at problems we cannot yet fully understand. But they raise a haunting possibility. What if the first generation of Martian children are born with disabilities we never anticipated? What if low gravity proves incompatible with human reproduction altogether? There exists a point of no return, a threshold beyond which adaptation to Mars becomes irreversible. We do not know exactly where that threshold lies. Is it after 1 Martian year, 5 years, a decade? Individual physiology varies, but the trajectory is clear. The longer humans remain on Mars, the more their bodies transform to match their environment. At some point, that transformation becomes complete. The colonist becomes Martian, biologically distinct from Earth humans, unable to return, committed permanently to a world that their presence has not changed, but that has fundamentally changed them. This gravity trap is not a flaw in our planning. It is a law of physics. It cannot be engineered away with better technology or overcome with human determination. Artificial gravity habitats could theoretically prevent these changes. But building rotating structures large enough to simulate Earth gravity on Mars would require resources and engineering beyond anything humanity has yet accomplished. We would need to construct entire spinning cities, vast centrifuges where colonists could spend hours daily maintaining their Earth physiology. The complexity is staggering, the energy requirements immense, and so we face an uncomfortable truth. Mars does not merely challenge our technology or our will, it challenges our biology itself. The very fabric of our bodies, woven through millions of years under Earth's gravity, begins to unravel under the lighter pull of the red planet. Those who choose Mars choose transformation, perhaps irreversible. They choose to become something other than what they were, adapted to a new world, but severed from the old one. As we contemplate establishing permanent settlements on Mars, we must ask not just if we can survive there, but what we become in the process. The gravity trap ensures that Mars will not be a second Earth. It will be something else entirely, inhabited by humans who are no longer quite human in the way we understand the term. They will be the adapted ones, the changed, living testaments to the fact that gravity is not just a force, it is a sculptor of life itself. Between Earth and Mars, the empty space looks harmless. A black canvas, a thin line on a diagram, a gap you could almost trace with your finger on a page. But that gap is not just distance, it is separation, it is delay. It is the quiet, uncomfortable realization that when you live on Mars, you are no longer part of Earth's daily conversation. You are a message in transit. At its closest, Mars and Earth are separated by more than 30 million miles. At its farthest, over 200 million. Light, the universe's fastest courier, takes between 4 and 24 minutes to cross that gulf, one way. A simple question becomes an experiment in patience. "How are you?" leaves Mars, rides a radio wave across the void, and almost half an hour later, an answer might return. This is more than an inconvenience. It is a fundamental break in how humans are used to existing together. On Earth, communication has become nearly instantaneous. A delay of seconds feels like a malfunction. On Mars, delay is the default. A conversation with family becomes an exchange of letters. A crisis becomes a series of voicemails. When something goes wrong, there is no real-time guidance, no live call with mission control, no voice in your ear saying, "Do exactly what I say." Imagine a medical emergency in a Martian habitat. A crewmate collapses. Their breathing is shallow, their pulse erratic. You trigger the emergency channel to Earth. Doctors at Mission Control receive the data minutes later, analyze, respond. Their instructions start the long journey back through space. By the time you hear them, the situation has already changed. The heart rhythm is different, the blood loss greater. The patient may already be gone. On Mars, call a doctor becomes be the doctor. Call an engineer becomes be the engineer. Every problem that happens must be solved by the people already there, with the tools they already have, under conditions they did not choose. Earth can advise. It cannot intervene. And it is not only time that separates Earth and Mars. It is timing. The orbits of the two planets are like gears in a slow, precise machine. They do not always line up favorably. There are only certain moments when the trajectory to Mars is short and the fuel cost small enough to be even remotely practical. Those moments arrive, on average, every 26 months. A launch window, a narrow opening in space and time where a rocket can leave Earth and reach Mars efficiently. Miss that window, and you are not just delayed by days or weeks, you are delayed by years. For a settlement on Mars, this creates a brutal schedule. Every 2 years and 2 months, you receive a shipment, or you don't. New people, or no one. Fresh supplies, or a gap in the chain. If a critical cargo mission fails shortly after launch, there is no backup rocket waiting on another pad, ready to go tomorrow. Another window must be prepared for, fueled, built. By the time it opens again, the colony may already have passed the point of survival. This is where distance stops being abstract and becomes intimate. Food on Mars does not mean fresh produce at the grocery store. It means calculated rations, shelf lives, growth cycles in fragile greenhouses. Every meal is a math problem. How much is left until the next resupply? What if that resupply never comes? The supply chain between Earth and Mars is not a chain at all. It is a series of single points stretched over years. One rocket, one chance, one set of containers trying to cross a void where there are no emergency landings, no rescue missions, no second trucks coming around the corner. If a ship carrying fertilizer, medicine, spare parts, and seeds is lost, the impact is not just financial. It ripples through every breath taken inside the habitat, every calorie eaten, every machine that must now run longer than it was ever designed to. In this fragile economy of survival, redundancy is life. But redundancy is also mass, and mass is the most expensive thing in space. To send 1 kilogram of anything from Earth to the surface of Mars requires rocket stages, fuel, guidance systems, heat shields, parachutes, descent engines, an entire ballet of technology, all to deliver a single small weight at the very end. Even with optimistic future rockets, the cost to land a kilogram on Mars will dwarf the cost to move a kilogram across any distance on Earth. A colony that depends on supplies from home is, by definition, a colony wrapped in debt. Energy debt, engineering debt, financial debt. Every extra spare part, every backup medical kit, every redundant water filter competes with something else. Do you send more food or more oxygen equipment? More scientific instruments or more tools to repair the ones you already have? An extra radiation shelter or the materials to build one yourself? These are not theoretical trade-offs. They are packing decisions that may decide who lives through a bad year. The dream of a self-sustaining city on Mars imagines a future where this supply chain fades into the background, where colonists harvest what they need from the planet itself. But even the most generous scenarios require decades, maybe centuries of dependence before true independence becomes plausible. In that long, uncertain period, a distant planet must function like a remote, understocked outpost that cannot call for help when the warehouse runs dry. Now, place yourself in the mind of someone living there. On Earth, isolation has limits. No matter how remote you are, you remain under the same sky, breathing the same air, held by the same gravity. Somewhere, beyond the horizon, cities hum, oceans move, storms form and fade. You are alone, but not removed. On Mars, you are removed. Look up, and the blue circle of home is a star-like point in the sky, sometimes bright, sometimes faint, sometimes hidden entirely by storms. Everyone you have ever known, every forest, every ocean, every history, every sound of traffic and rain and birds is compressed into a single pale dot. And that dot is not coming to you. Not now. Not soon. You send a message to your family. They will read it in several minutes. They send one back. You receive it during a different meal, a different sunset, a different day. The emotional rhythm of conversation fractures. Grief, celebration, conflict, all are stretched, softened, made strange by the lag. Emergencies amplify this sense of distance. A fire in a habitat module, a decompression incident, a radiation alert after a solar storm. On Earth, you might hear sirens, see flashing lights, feel the infrastructure of society closing in around you. On Mars, the infrastructure is a small group of people in pressure suits, the tools they carry, and whatever training they remember. Outside, there is only cold dust and thin air that will never fill your lungs. In that environment, the concept of home changes. Mars is not a neighbouring country. It is not even another continent. It is another timeline. The people there live out of sync with Earth, out of reach of Earth, subject to physics that does not care that we evolved to live in crowds, in families, in cities that can always, somehow, call for help. The distance problem is not a poetic exaggeration. It is the framework within which every other problem on Mars becomes harsher. Radiation is more dangerous when hospitals are planets away. A broken leg is more threatening when there is no air ambulance, no trauma centre, no specialist who can arrive in an hour. A failed crop is more frightening when the next shipment of seeds is 2 Earth years farther along its orbit. We sometimes talk about Mars as if it were a new frontier, like the oceans once were, or the early Americas. But those frontiers were, in the end, still on the same world. Ships could be built faster, routes improved, ports expanded. A message could take weeks, but eventually wires, then radio, then satellites compressed that delay. On Mars, light itself sets the minimum. There is no new technology that will let a voice arrive faster than physics allows. To live on Mars is to accept that, in any real crisis, you are already on your own long before the first alarm sounds. And that is the brutal distance we almost never talk about. Not the miles between planets, but the gulf between expectation and reality, between the way we live now, networked, connected, supported, and the way we would have to live there, delayed, dependent, and, in the moments that matter most, utterly isolated. If the journey to Mars is a test of engineering, living on Mars is a test of the human mind. Long before anyone steps onto Martian soil, we have already tried to simulate the experience here on Earth. In sealed habitats in the Arizona desert, on volcanic plains in Hawaii, in cramped mock spacecraft modules in Russia and China, volunteers have agreed to live as though they were on another world. No open doors, no fresh air, no stepping outside without a suit. These experiments rarely end the way their designers hope. In isolation, studies that last months, sometimes over a year, a pattern appears with unsettling consistency. At first, there is excitement, the novelty of the mission, the sense of importance, the feeling of being part of something historic. Then, slowly, the weeks begin to blur. Days feel interchangeable. Small annoyances sharpen. Sleep schedules drift. Some people grow silent. Others become irritable. Communication slows. Conflicts emerge over trivial things that, in any other setting, would dissolve in an afternoon. In several long-duration isolation experiments, crew members who passed rigorous psychological screening still reported depression, anxiety, disturbed sleep, and intense mood swings. Some spoke of feeling watched, even when alone. Others described a strange emotional numbness, as if their inner lives were running in low power mode. These were not untrained volunteers. They were often scientists, engineers, military officers, people used to discipline and stress, and yet they struggled, even knowing that outside their habitat wall lay not an airless desert, but a parking lot, a support team, and a quick way home. On Mars, there is no parking lot, no emergency door, only a thin shell of metal and regolith holding back a lethal world. Mars is not just physically barren, it is sensorially barren. On Earth, even in a quiet room, your nervous system is bathed in invisible variety, the faint vibration of distant traffic, the rustle of leaves, the complexity of natural light filtering through clouds and branches. Your brain is continuously fed a tapestry of input it has evolved to expect. On Mars, outside the habitat, the landscape is almost monochrome. Rust-red dust, dark rock, a thin pale sky, no trees to sway, no water to glisten, no birds crossing the horizon. The atmosphere is so thin that sound hardly travels the way we know it. The wind moves, but the world doesn't answer back with a familiar chorus of rustles and whispers that shape our sense of place. Inside the habitat, the environment will be tightly controlled, because it must be. Air composition, humidity, lighting, temperature, all regulated for safety. The same corridors, the same walls, the same rooms, perhaps a hydroponic garden, a few windows, if radiation shielding allows it, looking out on a landscape that barely changes day to day, year to year. At first, this may feel awe-inspiring. The red planet, framed in a viewport, will be unlike anything humans have ever called home. But the brain adapts. What is extraordinary quickly becomes background. The view that once took your breath away becomes just outside, and then, for some, a reminder. You cannot go there freely. You are surrounded by a vast, beautiful, lethal museum exhibit you can never truly walk through unprotected. This is a different kind of sensory deprivation. Not total absence, but narrow, persistent monotony. A uniformity of colour, sound, smell and texture that slowly thins the fabric of experience. We know from polar research stations, submarines and remote outposts that such monotony does not simply bore people. It can erode mood, distort time perception and weaken motivation. Tasks that once felt meaningful begin to seem arbitrary. The question, why am I here, shifts from philosophical to urgent, and you are not alone. That is its own challenge. A Mars habitat will be a social pressure cooker, a small group of people under continuous danger with no ability to truly get away from each other. Every personality trait will be amplified by confinement. Every conflict will echo in the closed space, unable to dissipate in the open air of another room, another neighborhood, another city. Social dynamics in small, isolated groups follow their own gravity. Alliances form, unspoken hierarchies emerge. Old arguments are never entirely over, they simply cycle in new forms. In Antarctic bases, crews have reported winter over syndrome, a cluster of symptoms including irritability, hostility, loneliness, and cognitive dulling that appears despite careful selection and training. Some become withdrawn, others domineering. Silence can become as sharp as shouting. On Mars, there will also be another presence. Earth. Not as a place you can fly back to, but as a delayed voice in your ear. Messages from mission control, from family, from friends will arrive minutes late, sometimes longer, creating a conversation that is always slightly out of phase. The comforting illusion of "we're in this together" is strained by a physics-enforced delay. Over time, the crew might begin to feel like actors in a show watched by a distant audience who never really understands the day-to-day reality of living inside a fragile shell on a hostile world. Resentment can grow, not toward one person, but toward the invisible collective of people back home who are safe under an open sky. Under constant risk, every mistake is magnified. Every misplaced tool, every half-checked reading can be the prelude to an emergency. Living like this, month after month, means your nervous system never truly rests. You may sleep, but your deeper mind knows that the wrong failure at the wrong time can end everything. That level of background stress is not a mood, it is a biology, reshaping hormones, sleep cycles, and decision-making. And there is one psychological weight that no Earth-based confinement study can fully simulate: the knowledge that there is no exit. On Earth, isolation experiments include an unspoken escape hatch. Participants know that if something truly goes wrong, if they break down, have a crisis, or simply cannot endure, they can be extracted. The door may be metaphorically locked, but physically it can always open. On Mars, the planet itself locks the door. Outside is an environment that will kill you in minutes without technology. Above you is a sky that might as well be stone, because the distance home is measured in months and millions of miles. Even if a ship were waiting and fueled, you could not go home in any meaningful emergency time frame. Psychological models describe this as learned entrapment, the internalization of the belief that escape is impossible. Prison psychologists know that hopeless confinement changes people. It doesn't simply create sadness. It breeds a particular mixture of resignation and volatility. Some withdraw so deeply they seem to vanish inside themselves. Others lash out, unconsciously testing the boundaries of a system they know they cannot leave. On Mars, the stakes of such reactions are higher than any prison. There are no extra guards, no backup staff, no replacement crew waiting just beyond the wall. The people you have are the only people you will have for a very long time. Mental health crises will come, not as dramatic television moments, but as slow descents. A crew member who stops participating in tasks, one who cannot sleep, another who becomes fixated on small grievances. Eventually, some will face the darkest edge of human psychology, the desire not just to leave the mission, but to leave existence itself. On Earth, when someone is at risk of suicide, a cascade of resources can be mobilized: emergency responders, hospitals, medications, family support. You can change their environment in hours, offer new people, new places, new routines. On Mars, the options are brutally limited. You cannot send someone to another city to start over. You cannot bring in new clinicians in person. Any psychiatric support from Earth will arrive as text and video, lagging behind events. The crew must become its own emergency room, its own therapy clinic, its own crisis hotline, while also being the patient, the colleague, the friend. Imagine trying to restrain someone intent on stepping into an airlock, knowing that any physical struggle risks damaging the very systems keeping you all alive. Imagine the aftermath, confined with the memories, the guilt, the questions, with nowhere to go to escape the place where it happened. On Mars, you cannot walk away from a room. The habitat is the room. And then there are the people for whom Mars would not be a daring assignment, but a childhood. If a settlement survives long enough, children will be born there, taking their first breath in recycled air, their first steps in 1/3 gravity. For them, Earth will not be home. It will be a distant concept, a blue light in the sky, a source of stories and images. Their playground will be corridors. Their seasons will be mission cycles. Outside will be something that always requires armor. Growing up in such an environment means internalizing danger as normal. The idea that a wall failing, a valve sticking, or a minor oversight could kill your entire family is not an abstract plot point. It is part of the bedtime story of your life. How does a child develop a sense of safety when safety is a continuous engineering achievement, not a background condition of nature? Their social world will be minuscule. A handful of adults, a few other children. No anonymity, no chance to reinvent themselves at a new school, no broader community to disappear into while they figure out who they are. Identity will be shaped under a microscope. Every change, every rebellion, every mistake noticed. Some may thrive, becoming resilient in ways Earth-raised children rarely need to be, but others may feel a quiet, unresolvable grief for a world they never knew, a world where rain falls, where oceans exist not as lessons, but as sensations, where going outside is not a classified operation. We often imagine settlers gazing at Earth from Mars with pride, thinking, "We did it. We made it here." Another thought may emerge with equal strength. They did not choose this. The children born on Mars will inherit not the dream, but the reality. Not the inspirational posters, but the sealed doors. And the question hangs in the thin Martian air. What happens to the human mind when a planet becomes a lifetime sentence, even if we call it home? Mars tests our technology, but it also tests something subtler and less predictable: the capacity of human consciousness to endure being permanently cut off from the deep, quiet abundance of Earth, the soil of forests, the chaos of cities, the infinite randomness of strangers, the feeling, perhaps more important than gravity itself, that if we truly needed to, we could always walk away, and the sky would still be there, waiting. We like to imagine the first city on Mars as a gleaming outpost of human ingenuity. Domes of glass, corridors of light, dust-streaked windows looking out over a red horizon. But behind every window, behind every airlock and pressure seal, there is a quiet question that refuses to go away. Who paid for this? And more importantly, why? To build the first true colony on Mars. Something beyond a short-lived scientific base. Something that can house thousands with redundancy, safety, and long-term infrastructure. Estimates range from $100 billion to well over $1 trillion. Numbers so large they stop feeling real. Numbers closer to global wars and entire national healthcare systems than to any construction project we've ever attempted. A single heavy-lift rocket costs hundreds of millions of dollars. A fleet of them, flying regularly, stocked with life support systems, habitats, spare parts, medical facilities, radiation shielding, power stations, oxygen plants, water processing units, food production modules, rovers, spacesuits, and emergency backups for each of those systems. That is not a line item on a government budget. That is a redefinition of it. We sometimes speak about Mars as if it were the next frontier in real estate, as if we just need to get there, claim some land, and the rest will follow. But there is a fundamental difference between settling a new continent and trying to occupy a dead planet. On Earth, when people moved into unknown territories, they brought some supplies, but they also brought an assumption: the land itself would support them. Forests would provide wood. Rivers would offer fish and water. Soil, however rough, would eventually yield crops. Mars offers none of that. Everything that keeps a Martian colonist alive must be manufactured, shipped, or painstakingly extracted and maintained with advanced machinery that itself must be shipped and maintained. Oxygen, water, food, shelter, pressure, warmth, medical care, communication links, spare parts for spare parts. Each of these is a cost that never truly ends. Economists call this operational expenditure. On Mars, it is not a background detail, it is the main character. And in this story, there is a missing piece: return on investment. When we invest extraordinary amounts of money into any project, there is usually some expectation of value coming back. Sometimes that value is financial. Sometimes it is political power, national prestige, scientific knowledge, or security. The Apollo program, enormously expensive, bought not only lunar samples, but decades of soft power, technological innovation, and a powerful story of national achievement. Mars promises wonder, yes. It promises discoveries and data and new perspectives on our place in the cosmos. But as an economic engine, Mars is a quiet world. There is no resource we currently know of on Mars that is both essential enough and rare enough to justify shipping it back across tens of millions of kilometers of vacuum. Iron, we drown in it on Earth. Water, we have it here in quantities that are vast and cheaply accessible compared to melting dirty ice under Martian regolith. Exotic metals, If they exist in rich ore bodies, they are almost certainly more expensive to extract and transport from Mars than from Earth, asteroids, or the deep ocean. Every kilogram launched from Earth costs money. Every kilogram landed gently on Mars costs more. And every kilogram that would have to be lifted back off Mars and flown home would be so expensive that the cargo would need to be almost unimaginably valuable, more precious than gold, more indispensable than oil. So far, no one has found such a cargo. Sometimes the argument shifts. Perhaps Mars will not be a mine, but a test bed, a place to build technologies that later pay off on Earth. Closed-loop life support, advanced recycling, autonomous construction. These are real possibilities. But here is the unsettling part. We do not need to go to Mars to build any of them. We could develop closed ecosystems in deserts on Earth at a fraction of the cost with far less risk. We could practice fully automated construction in hostile but terrestrial environments. The research benefits of Mars are real, but they are not economically unique. The same breakthroughs can be pursued without committing to sustain a population in an airless, frozen wasteland. To understand the scale of this economic mismatch, we can look south, not up. Antarctica is cold, isolated, and hostile. Yet compared to Mars, its challenges are gentle. It has gravity identical to ours, an atmosphere, liquid water, and a protective magnetic field. Though brutal, it is still Earth. A place where you can breathe with a mask instead of a spacesuit, where stepping outside without a pressure vessel does not kill you in seconds. Antarctica has resources, fish, potential minerals, even areas of exposed ground. It is closer to major cities than Mars will ever be. A single flight can reach it in hours. Communication is instantaneous. Rescue is difficult, but possible. And still, after all this time, Antarctica has no true cities. It has research stations and temporary crews, populations that come and go with the seasons. Almost no one raises a family there. No one retires there. No one calls it home in the way we mean when we speak about colonizing a place. Why? Because it is expensive to live in a place that does not support human life on its own. Because the benefits gained from permanent settlement do not outweigh the costs. Because when the environment is too hostile, there is no economic gravity keeping people there once funding dries up. If we will not build a permanent city in Antarctica, with the oceans a flight away and air waiting just above our heads, what makes us think we will build and maintain self-sustaining cities on Mars, where every mistake is fatal and every breath is imported? In recent years, some of the world's richest individuals have spoken eloquently about becoming a multiplanetary species. Their rockets are impressive, their engineering teams brilliant, their ambitions sincere. But ambition cannot change physics, and it cannot erase balance sheets. Rockets can become cheaper. Launch costs can fall. Mass production can drive down the price of habitats, life support systems, and power units. However, none of this changes the underlying reality that a Martian settlement would remain an economic sink for the foreseeable future, a continuous drain of materials, money, and expertise from Earth to keep a fragile population alive on a world that does not want them. Promises of 1 million people on Mars often glide over dull details. How many tons of equipment must be shipped per person? How often do we replace worn-out machinery choked with Martian dust? How do we fund decades of shipments when political priorities change, economies slump, and successive generations of taxpayers begin to ask a quiet, dangerous question? Why are we still paying for this? The sustainability problem of Mars is not just about growing enough food or recycling enough water. It is about staying funded. A colony that cannot pay for itself must forever rely on the generosity, curiosity, or vanity of people on another world. If that support falters, the colony does not become poorer, it becomes uninhabited. In this light, self-sustaining on Mars does not mean inspirational slogans. It means something brutally specific, no longer dependent on Earth for essentials, not just for food or water, but for replacement electronics, pharmaceuticals, precision tools, industrial lubricants, high-grade alloys, computer chips, medical imaging equipment, and everything else that modern high-tech life invisibly rests upon. To build all of that on Mars, from Martian soil and air, would require an industrial base so large that the colony would already be more like a second civilization than a frontier town. And building that civilization would require the very thing we were trying to avoid: a staggering, prolonged economic subsidy from Earth. If we step back from the romantic glow of red sunsets and imagined domes, another path quietly emerges. One that still uses those vast budgets, that still embraces exploration and technology, but points them in different directions. With $1 trillion, we could accelerate clean energy across the globe, transforming entire power grids and reducing the planetary risks that make backup worlds feel urgent in the first place. We could fortify coastal cities against rising seas, prevent famines, abolish diseases that still kill millions every year. We could build telescopes that peer back to the dawn of time, probe the icy moons of Jupiter and Saturn for hidden oceans, or scatter a fleet of sensors through the asteroid belt to map resources and origins with unprecedented detail. We could surround Earth with a shield of monitoring satellites to anticipate climate shifts and natural disasters with exquisite precision. We could construct massive space-based observatories, platforms in orbit that would become the staging grounds for every future step outward, making any eventual Mars mission safer, cheaper, and more informed. None of this has the simple romance of a colony on another world. It does not fit neatly on a poster or in a billionaire's keynote slide. But it may bring us closer to a future where our presence in space is not a fragile act of defiance against a hostile environment, but a natural extension of a thriving civilization that learned to stabilize its first home before attempting to build another. The narrow corridors of Martian economics force us to confront an uncomfortable possibility. Perhaps the most responsible way to prepare for a multiplanetary future is not to rush into a red desert and dare it to support us, but to invest in a web of technologies, infrastructures, and protections that make our first planet truly sustainable. For now, Mars is a dream with a price tag written in stars and scarcity. We can reach it. We may even walk on it, study it, and build outposts that flicker on and off like seasonal camps in the frozen south. But to live there, truly live there, in cities that grow and endure, that is not just an engineering challenge, it is an economic one. And in the quiet arithmetic of cost and return, Mars remains less a new home and more an exquisitely distant, exquisitely expensive museum of what worlds can be when life never came. We have spent this journey dismantling the fantasy of Mars as a new Earth, peeling back each comforting layer until only the harsh machinery of reality remains. But this is not a story of abandonment. It is a story of correction. Mars is not the end of the dream. It is a signpost telling us we have been looking in the wrong direction. Humanity's future in space was never meant to be chained to a dead planet. It was meant to unfold in places where physics, engineering, and biology can finally agree. Places not carved from hostile rock, but constructed from first principles. Not worlds we inherited, but habitats we design. Imagine a city in space that does not sit on the surface of any world at all. It hangs in the darkness like a slow-turning lantern, kilometers long, its outer shell rotating with silent precision. Inside, down, is no longer toward a planetary core, but toward the hull itself, created by centrifugal force. This is an O'Neill cylinder, a concept proposed in the 1970s by physicist Gerard O'Neill. An artificial world built in orbit, not bound to the compromises of Mars, or the storms of Jupiter, or the crushing pressures of Venus. Here, gravity is adjustable, not a permanent injury like Mars's 1/3 pull, but a dial we can set. Need Earth gravity to preserve bones and muscles. Spin the cylinder at the right rate. Need lower gravity sections for manufacturing or medicine. Build interior rings that turn more slowly. Physics becomes a design parameter, not an unchangeable threat. The atmosphere inside is not a razor-thin toxic whisper like Mars, but a deliberately crafted mixture held behind meters of shielding. No global dust storms, no planet-wide cold snaps, no perchlorate chemicals laced through the soil. If the air becomes unsafe, we know exactly where every molecule came from and how to change it. Outside, thick layers of rock and slag harvested from asteroids form armor against radiation. Instead of burying ourselves under Martian regolith and hoping it's enough, we wrap our habitat in deliberate protection, calculated and tested. We are no longer guests in a hostile land. We are architects of our own sky. Inside, vast windows, protected by angled mirrors and shutters, could pour in filtered sunlight. Cylindrical valleys rise up on both sides, fields and forests curving overhead until they meet above you. Rivers flow along the inner surface, held in place not by a planet's pull, but by the spin of the world itself. Day and night are no longer dictated by a distant sun and a tilt of an axis, but by shutters and mirrors we control. If crops need more light, we adjust. If people need longer nights, we dim the world. Here, the problems that break Mars become malleable. Gravity is set, not suffered. Air is mixed, not scavenged. Water is cycled, not desperately scraped from buried ice. We move from surviving in an alien ecosystem to engineering one from scratch. But how do we get there? We begin closer to home, where the path is shorter and the feedback faster. Not with a red planet, but with a grey, silent neighbour that has circled our world since before there were eyes to see it. The moon is not friendly, but it is honest. It does not pretend to be habitable. There is no thin lie of an atmosphere whispering promises it cannot keep. There is only vacuum, dust, and rock. And yet, in its starkness, it offers something Mars cannot: proximity. A lunar base is 3 days away, not months. A distress call is not a final confession. It is a prompt for a launch window. If something fails, if a habitat ruptures, if a system malfunctions, rescue is not impossible. It is merely urgent. Time delay to Earth is measured in seconds, not minutes. Conversations with mission control are not monologues, but dialogues. A surgeon on Earth can guide a robotic arm on the moon with almost real-time precision. An engineer can hear a problem, ask questions, respond, adjust, while the situation is still unfolding. The moon also holds resources we understand how to use. Water ice tucked away in permanently shadowed craters. Oxygen locked in the minerals of its regolith. Metals, silicon, and the raw materials for building. 380,000 kilometers away instead of tens of millions. A lunar base is not a romantic second Earth. It is a workshop. A classroom for learning how to live off-world without the illusion of a ready-made environment. It is where we will discover what breaks in long-duration habitats. what people need psychologically when there is no sky, what closed-loop life support systems really do when they run not for months, but for years. The moon is not an escape. It is a rehearsal. Beyond it spreads something even more valuable than alien landscapes. A sea of raw materials drifting in the darkness between Mars and Jupiter. The asteroids. Where Mars demands sacrifice and offers little in return, the asteroids whisper a different bargain. They do not try to be homes. They offer instead to be mines, workshops, and fuel depots. Some asteroids carry metals richer than anything found in Earth's crust. Iron, nickel, cobalt, traces of platinum group elements concentrated over eons. Others may contain vast reserves of water in the form of ice, water that can be split into oxygen for breathing and hydrogen for fuel. In a future where rockets refuel in orbit instead of leaving Earth fully loaded, asteroids are not obstacles. They are gas stations. From these drifting worlds, we could build the shells of O'Neill cylinders, station components, radiation shields. We would no longer drag every kilogram of metal up from Earth's gravity well. Space industry would evolve from a supply line to a local economy. In this vision, the economic value of space does not come from selling tickets to die slowly on Mars. It comes from building infrastructure that multiplies our capability everywhere else, in orbit around Earth, around the Moon, in the quiet Lagrange points, where gravity finds its delicate balances. And in all of this, there is another quiet revolution happening. A future where our bodies do not have to go everywhere our curiosity does. Already, fleets of robots prowl Mars, roll across the Moon, skim the clouds of Venus, and plunge into the atmospheres of gas giants. They do not need shelter, air, or gravity. They do not panic if the sky turns black and the temperature falls to 100 degrees below freezing. They wait. As communication technology advances, our presence on distant worlds may become less physical and more virtual. High-bandwidth links, better autonomy, and immersive interfaces could allow scientists to explore an alien world from orbit or even from Earth. Seeing through robotic eyes, feeling haptic feedback from robotic hands, steering drones through canyons we will never breathe in. On Mars, a person on the surface must spend enormous resources just to exist. A robot requires power, maintenance, and software updates. One risk is catastrophic. The other is inconvenient. This does not erase the value of humans in space. It refines where they should be. Human presence becomes precious, reserved for places where our bodies and minds make the most difference. In orbital stations, in lunar labs, in habitats where we can stay alive long enough to learn. There is another question lingering behind every promise of Martian colonies. What do we sacrifice here on Earth when we chase a mirage there? Every dollar, every hour, every genius mind devoted to building closed life support systems on a planet that will try to kill us forever is a resource that could also be used to heal the only biosphere that currently sustains life as we know it. Learning to scrub carbon dioxide efficiently in a spacecraft can teach us to capture it from the atmosphere at home. Perfecting water recycling for a moon base can inform systems for arid, warming regions on Earth. Designing dense, self-sufficient habitats in orbit can guide how we might build cities that use less land, less water, less energy. We do not have to choose between Earth and space, but we do have to choose what kind of space future pulls us forward. One that treats Mars as a lifeboat, or one that treats Earth as the irreplaceable origin and space as an extension of its reach. This is why research outposts are different from permanent settlements. A research station on Mars or the Moon or in orbit is built with an understanding. It is temporary, contingent, limited. Its purpose is knowledge, not population. People rotate through, return home, share what they've learned, and send the next crew better prepared. Logistics chains are long, but not endless. When conditions change, missions evolve or end. A permanent settlement, by contrast, must close its own loops. It must imagine children growing up, aging, dying in a place where the environment was never designed for human life. It must confront the ethics of bringing new people into a world where escape is nearly impossible and survival is not guaranteed. Research outposts are humanity stretching. Colonies on Mars, at least with our current understanding of biology and environment, would be humanity tearing. The alternative future is quieter, more patient, and far more powerful. It unfolds not on the rusty plains of Mars, but along orbital paths, in spinning habitats, on the airless slopes of the Moon, and inside machines that walk alien soil in our stead. It is a future where we do not flee Earth, but learn from it, where we expand into space, not because our planet failed us, but because we finally understood it well enough to carry its lessons with us. Humanity does not belong on Mars, not yet, and perhaps not ever in the way we imagine. We belong where we can build, adapt, and thrive without betting everything against the cold indifference of a dead world. We belong in engineered skies that tell the truth, in habitats that admit they are fragile and therefore designed to be strong. In a solar system where we move not as desperate refugees, but as careful apprentices of physics, chemistry, and life itself. The dream is still there. It was just never about turning Mars into home. It was about turning ourselves into a species that knows what home really means. We have wandered across a hostile horizon, thin air that cannot sustain a single breath, radiation that seeps through metal and bone, water locked away in unforgiving ice, soil that is more poison than promise, gravity too weak to keep a body whole, and a distance so vast that help is not delayed, it is erased. The dream of millions living beneath a Martian sky begins to dissolve, not in cynicism, but in contact with reality. Accepting this is not surrender, it is orientation. Every explorer in history has had to confront a map's hard edges, the places that could not be crossed, not yet, not with the tools they had. Wisdom was not in pretending those mountains were smaller, or those oceans more gentle. Wisdom was in looking honestly, then charting a course that life could actually survive. To admit that Mars may never be a second Earth is not to shrink our dreams, but to refine them. Mars resists us at every scale: biological, psychological, economic. It does not offer air, pressure, magnetism, bacteria, or ecosystems to bend to our will. To build a true city, there is not just difficult. It is a perpetual emergency dressed up as a frontier. A colony would not be a new world. It would be a lifetime inside a carefully managed failure state, where a single broken valve, a single missed shipment, a single unanticipated feedback loop could unravel everything. Yet this does not mean Mars is a mistake. Mars is a mirror. It reflects our limits back to us, of our bodies, our technology, our patience, our money, and our myths. And in doing so, it becomes invaluable. We do not need to call Mars home for it to shape our future. We only need to listen to what it is quietly telling us. Exploring Mars, robotically, and perhaps with brief, careful human visits, may be one of the most important things we ever do. Under its rusted skies, we learn how planets live and die. We learn how atmospheres are lost, how magnetic fields fade, how water migrates and disappears. we learn how fragile a habitable world really is. Those lessons do not belong to Mars. They belong to Earth. The truest colony we will ever build is not on another planet, but in our understanding. The archives of data, the maps of ancient riverbeds, the chemical signatures of long-vanished seas, these are foundations of a future where we finally know what it takes to keep a world alive, and what it costs when we fail. And perhaps humanity's long future in space will not look like red deserts and domes, but like something stranger and quieter. Vast habitats orbiting in sunlight all year round, built where gravity can be chosen instead of endured. Cities not buried under regolith, but unfolding in the emptiness between worlds. Mars then becomes not the destination, but one stop in a much larger architecture, an object of study, not of permanent settlement. In that sense, the dream we should actually pursue is not escape, but comprehension. To understand our solar system so deeply that we stop treating Earth as a disposable stage and start recognizing it as the rarest artifact we will ever hold. To use Mars as a teacher, not a lifeboat. To accept that some worlds are meant to be visited, not inhabited. If this journey through the harsher side of the Mars dream kept you company tonight, you can help this story reach others. Tap like if you found yourself thinking in new directions. Let me know in the comments where in the world you're listening from, your small point of light on this planet's surface. And if you'd like to drift through more cosmic nights together, you can subscribe so you don't miss the next voyage. There is also an optional channel membership for those who want to quietly support these long, slow explorations. It's never required, always appreciated. For now, let Mars keep its silence. Our task is here, one fragile world, under one thin sky, in one brief moment of cosmic time, trying, with open eyes, to learn enough that we never need a second chance.